morning, guys. My name is FARHAN, and my teammates are Logan and IQBAL. So we are from Group 12, and today in this video, we'd like to talk about experiment 17, which is the title is fluid friction measurement, which is basically we measure the fluid friction inside the pipe, inside the fitting, and so on. So without further ado, let's jump into the introduction of the experiment. So as you guys know and can see on the screen, so when fluid flow through a circular pipe, there will be a pressure drop. So mainly the pressure drop is due to the friction, and this can be represented by fanning equation, which is, as you guys can see on the screen, delta P equal to 2 times F times U square LPO divided by D. So delta P is the pressure drop due to friction, F is the fanning friction factor, U is the average velocity of the fluid, L is the length of pipe, rho is the density of the fluid, and D is the inside diameter of the pipe. This equation basically can be derived from the Bernoulli equation, and unfortunately we will not be discussed in here. So this equation also can be written in the form of head loss as a subject. So head loss is actually the pressure drop. Is there another name for it? So head loss is equal to delta P divided by density and G, which is the gravitational acceleration, and equal to the previous part of the equation. So at different flow rates, starting from the weakest to the turbulent region. So as you guys know, so when the fluid flow through the pipe, they have a flow profile which is the parabolic. So they are starting from the lamina to the turbulent region. Head loss can be measured experimentally, and corresponding fraction can be calculated, which is what we'll be discussing here and that we have done in the experiment. So next, let's jump to the experiment setup. So as you guys can see on the screen, there is the actual experiment setup. We have a lot of component here from number 1 to the number 25, and then we have some the number here which is the V. This is actually the yeah. So let's jump to the schematic diagram. So as you guys can see, this is schematic diagram, and we have like 25 part of it. So the first important part is the water, because the process spring in this experiment is water, so the water must be fed from the top, which is from the hydraulic bench. So number 2 to number 15 is actually the different type of fitting. They have like different shape, different geometry, and of course a different K factor. So as you can see on the middle on the screen, which is number 17, 18, and 19, they are actually a device that measure the flow of the fluid. They are pitot tube, venturimeter, and orifice meter. So moving on to number 19 to the number 35, they are all basically fitting which have different kind of shape, similar to the one that I have talked earlier.
So I will continue on the objective for this experiment. So basically the main objective for this experiment is to study the fluid friction losses for an incompressible fluid flow through pipes, fittings and metering devices. As we all know, there are 4 parts in the experiment, which is part A, friction loss to straight pipes, part B, friction loss to fittings, part C, friction loss due to area change, and part D, frictional loss to flow meters. So for this section A, the objective is to measure a series of head loss at different flow rates to the 3 smooth bore test pipes. For experiment D, the objective is to determine the head loss associated with flow of fluid through standard fittings in experimental rig. While for experiment C, the objective is to find out the frictional heat loss due to sudden expansion and contraction in the pipeline. While for part D, the objective is to measure the average velocity and flow rates in pipeline by application of differential heat obtained by flow meters.
Hi, so I will explain about the procedure for this experiment. So actually, this experiment have four parts. The first one, experiment A, is about the frictional loss through straight pipes. Experiment B about the frictional loss through fittings. Experiment C about the frictional loss due to flow area change. And experiment D about the frictional loss through flow meters. Let's look in detail about experiment A. So the first thing is the pipe network is to need to be flow with water, and we need to set the volumetric flow rate first and in the beginning of the experiment. Second, corresponding valves are to be open or closed to obtain the flow of water through the test pipe. So let's say we want to test the pipe number one, so we open the valves on that pipe, on that particular pipe, and we close the other valves. Next, the frictional head loss is measured at corresponding pair of pressure tapping with manometer. So actually in the real lab later they will have a tapping where that's the point where we will measure the frictional head loss. Next, the internal diameter of the pipe is measured using a slide plug caliper. The steps are repeated with a different volumetric flow rate. And also after we done for pipe 1, we move on to other test pipe with the same procedure. And the collected data are filled in the table below. As you can see, the velocity, log U is also the velocity, and log delta H are to be calculated. And log U and log delta H will be used to make a graph later on. The friction factor is to be calculated to be plotted against Reynolds number, and the calculated head loss will be compared with the head loss that we obtain from the manometer reading. So next for experiment B. So actually the first and second step is same like experiment A. The the corresponding valves are to be open or closed to obtain the flow water through the required fittings. Experiment B, we will focus on fittings. So for each test fittings, differential head between two tappings are to be noted at different flow rates. So the head loss also to be noted for each test valve with corresponding flow rate. And the result for this experiment is is to establish that the value of K for a particular fittings or valve is constant over the flow range tested. So next, experiment C. Same procedure for number 1 and 2. Corresponding valves are to be open or closed to obtain the flow of water through the required expansion or contraction section. So for each section, heat loss is to be noted with corresponding flow rate. The K factors value is to be calculated and tabulated for different flow rate. So for experiment D, same procedure for number 1 and 2. The corresponding valves are to be open or closed to obtain the flow of water through the particular flow meter. So actually for experiment D, we have two type of flow meter, the ventrimeter and also the orifice meter. So the measurement of flow rates is to be done in conjunction with flow control valve. In the diagram, you can see it labeled as V4, and the differential heat loss will be measured between the tappings. Either we use the mercury or pressurized water manometer. And the flow rates obtained from the heat loss measurements will be compared with the flow rates obtained experimentally. So lastly, the readings for both orifice and ventrimeter are to be obtained and tabulated in the table. So I think that's all for the procedure.
So we proceed to the result part. So as you guys have see the video about the procedure, so here is the result for the experiment A, which is the frictional loss through the pipe. So we are using 4 different kind of pipe with different diameter. The volume, time, and the flow rate is being determined during the experiment, and the rest of them can be calculated by using some specific formula. So we repeat it 3 times because we want to get a more accurate result. So one thing to be noted is that the Reynolds number for all these run are actually turbulent. Yeah. So next we go to the frictional loss due to the fitting. So we have like 8 different kind of fittings, starting from the gate valve, 45 band, and so on. So we also do it 2 run for this experiment, and the differential pressure is actually the reading that we get from the manometer, and pressure drop is we convert it actually. And we also all of these also can be calculated by using some specific formula, and here are the K value that we calculated. So one thing to be noted is that some of them have slightly larger K value, or some of them have very small K value. So this is due to the shape of the fitting. So next we go to the experiment C, which is the frictional loss due to the area change. So which basically in this experiment we are using contraction, and we are experimenting contraction and expansion. So yeah, from small diameter to the big diameter we call it expansion, and from the big diameter to the small diameter we call it contraction. So we fix the volume and the time we vary it, and we have 2 velocity because we have 2 diameter, and the differential and at the end is actually the reading that we got. So here are the K value, but we only have the K value for the contraction. We don't have the K value for the expansion because I think it's negligible. So let's move on to the last result, which is the frictional loss through the pipe. So in this part of the experiment, we are using 2 different kind of flow meter, which is the orifice meter and the venturi. So each one of them we run it 3 times, and we fix the volume to the 0.09, and we vary the time so that we can have like different flow rate. So the pipe diameter and diameter is being fixed, of course, because we didn't change to another kind of orifice or venturi meter. And the differential pressure is being determined by the reading of the manometer, and here are the calculated flow rate. So as you guys can see, the flow rate are pretty much similar, but they have like a slightly different. What we have here is the graph for the experiment A, which is we've plotted a graph for log velocity versus the head loss. So as you guys can see on the screen, the graph is like that. It's actually a bit weird. So as you guys can see, type 1 has highest amount of logarithm of log u, while type 4 has the lowest amount of log u. So we also have a second figure, which is the fanning friction versus Reynolds number. So as you guys can see, type 4 has the highest fanning friction compared to the other pipe, but pipe 4 also has the smallest Reynolds number. On the other hand, pipe 1 has the largest Reynolds number, but its friction loss is actually quite small.
So next, I will explain about the calculation of data for experiment A, B, C, and D. So this is actually as the example of the calculation. So for experiment A, the first thing that we need to do is we find the flow rate, which is volume over time. So actually the flow rate will be set by us during the experiment. So we need to set the level of the water and we measure the time taken for the water to fill until that level. So actually we find the flow rate manually, and then we find the velocity equal to flow rate over area. We find the head loss, which is delta H equal to pressure drop over rho G. And then we find the calculated Fanning's friction factor, and we assume the length of the pipe is 1 meter. So the formula F equal to delta H G D over 2U squared multiplied by L. And then we find the Reynolds number, RE equal to du rho over mu, and we calculate the head loss delta H, 2 multiplied by F theoretical multiplied by U squared and L divided by GD. So we can see the number 3, we find the head loss from the experiment. Number 6, we find the head loss theoretically, and then we can find the absolute error. For this example, our absolute error is around 0.25%. So we will move on to experiment B. This example, the value are based on the data of the gate valve. First thing we need to do is we find the head loss, pressure drop over rho G, and then we find the velocity U squared over 2G. So as we know the experiment B, we want to find the K coefficient. The third thing we need to do is we find the K equal to 2G delta H over U squared. And for experiment C, so we want to find the head loss. So before we find the head loss, we need to find the volumetric flow rate, and then we find the velocity at larger cross section, volumetric flow rate over area, and also we will find the velocity at smaller cross sectional area. So head loss equal to U1 minus U2. U1 is the velocity at larger cross section, and U2 is the velocity at smaller cross section, squared divided by 2G. So for experiment D, we want to find the flow rate from the head loss obtained, and we want to compare it with the flow rate um, that we already set in the beginning of the experiment. So firstly, find the flow rate, volume divided by time, and then we find the velocity at upstream pipeline, which is EUA, flow rate over area, and we find the head loss, delta H equal to pressure drop over rho G, and we find the velocity at orifice throat, U naught. So the constant already given 0.62, so then we can find the velocity at orifice throat with the equation, and then we find the calculated flow rate with the orifice diameter equal to 0.02 meter, which is given in the lab manual. So when we find this flow rate, we will compare it with this flow rate. So next, for venturi meter, we find the velocity at upstream pipeline, UA, equal to flow rate over area, and then we find the head loss, pressure drop over rho G. We find the velocity at venturi throat, UV, and CV is given which is 0.97, and we can find UV with this equation. So and lastly, we find the calculated flow rate with the venturi diameter dV equal to 0.016 meter. So then we will compare the Q calculated with the uh, with the flow rate that we already set in the experiment. So that's all for the calculation of data.
So let's continue on the discussion of the result of this experiment. So let's start with experiment A, which is frictional loss through step. So in this experiment, the head loss is calculated by using a different flow rate of water across the smooth bore pipes, and throughout the experiment, the different flow rate of water is used in each type of pipe. So basically, this experiment is conducted to determine the pipe which have a rougher internal surface. Since pipe 3 and pipe 4 has the same internal diameter, the flow rate between the pipe 3 and pipe 4 is compared. So based on the example, we found that the pipe 3 has a lower flow rate. So we decide that the inner part of the pipe 3 is made up of roughened surface. Based on the theory, it shows that if water flow through a rough surface, the water will have a lower flow rate. Then the pressure drop across the pipe is measured by using the manometer. Then the calculated head loss by using the recorded pressure drop is compared with the theoretical head loss. So these are the data we obtained throughout the experiment A. Based on the table, the relationship between the velocity and the head loss is as the velocity of the fluid in the pipe increases, mostly the head loss also increases. This is why because when the velocity across the pipe increases, it will increase the frictional force against the fluid, and the frictional force causes the head loss of the flowing fluid in the pipe. At some points, if we notice, the calculated friction fraction is inversely proportional to the Reynolds number, which it obeys the theory, but sometimes the fanning factor increases with the Reynolds number due to errors such as the readings in the manometer is keep changing. Based on the table, at some points the head loss increases and the pipe internal diameter decrease, which obey the theory, except for the diameter 0.0047 meter. This is why because at this lower diameter the head loss was recorded to be lower because there is an error when reading the manometer. So let's continue on the experiment B, which is frictional loss through the fitting. So basically this experiment is conducted to calculate the head loss when the water flows through the fittings such as bands, valves and elbows. So when the water flows through these fittings, there would be a significant pressure drop due to change in the water flow direction. So the equation we use to determine the head loss is this, and to determine the loss of cohesion we use this formula, and to determine the head velocity we use this equation. So from the data we found that each fittings recorded a different value of head loss. Based on the data, it shows that the head loss value is directly proportional to the velocity head, and this means that the theory is obeyed. So these are the data we obtained from the pressure drop and the velocity head of the water flow through the various fittings. So from the data we study that a gate valve has recorded the highest average head loss of pressure drop. This is why because when the water flows through this gate valve, there is a change in direction of the water flow. So this causes the water flow become turbulent suddenly, and it will consume some energy. So the head loss will be resulted due to loss in momentum of the water flow. So at the same time, when we notice the 90 bend fitting, it recorded the lowest pressure drop. So our group found that there might be an error when recording the data of the 90 bend fittings, such as parallax error or a small leakage in the pipeline, because theoretically 90 bend fittings should have a higher head loss or pressure drop. This is why, because when the water flow through the 90 bend fittings, the water flow will become more turbulent and will result in the higher pressure drop. So under this turbulent condition, the pressure drop increases as the flow rate increases, and the loss of coefficient are varied for each fitting as long as the velocity are also different due to flow rate. So let's have a look on the experiment C, which is frictional loss due to flow area change. So in this experiment C, we determine the frictional head loss due to sudden contraction or expansion in the pipeline. Based on the theory, it shows that when there is a change in the pipe diameter or there is a sudden contraction or sudden expansion, it would be causes additional head losses or pressure drop due to formation of eddy current in the fluid flow. Based on table C, it shows that when the water flow into a sudden expansion, the head loss is higher and it is increasing as the flow rate increases. This happens because when the fluid flows into a sudden enlargement, the velocity decreases suddenly, and this will produce a higher energy loss and because of a turbulence flow produced. When the fluid flows into a sudden contraction, it will result increase in the velocity and consequently a greater pressure drop is created. Based on the data, it shows that the head loss in the sudden contraction is higher compared to a sudden enlargement head loss. This happens because when the fluid that flows in the streamline flows closely to each other and converge, it will create a turbulence flow. So the area of the pipe is inversely proportional to pressure loss. So these are the data we obtained throughout the experiment C. When we notice from the data, in sudden enlargement, the loss coefficient are not calculated. This is why, because there might be an error occur when recording the data, such as parallax error or a very small leakage of water in the streamline that will affect the result. So I will continue on the experiment D, which is frictional loss through flow meters. So in this experiment, the objective is to measure the head loss of flowing fluid in both orifice meter and the venturi meter. So in the experiment, a different flow rate is used to measure the head loss of fluid flow across the meters. Based on the theory, it shows that an orifice meter has a medium heat loss compared to a venturi meter due to sudden contraction at the end of the meter. So below shows the equation to determine the head loss and the total velocity of an orifice meter, and equation to determine the total velocity of a venturi meter. Based on the data obtained, the pressure drop of the water at the different flow rate across the venturi meter is higher compared to a orifice meter. Thus, the head loss of the flowing fluid in the venturi meter is also higher. So this means that the data collected from the experiment is not obeying with a theoretical statement. Even though when we compare the head loss of the both meter, in some points only in orifice meter there are some small increase in the head loss at the medium flow rate. This shows that the result from the orifice meter in some ways obeys with the theory. So these are the data we obtained from the experiment D. Then when we compare the flow rates obtained from the experiment and the calculated flow rate, most of the values are showing a big difference. This means that During the experiment, there are few errors has been encountered. For example, the error might be due to parallax error while measuring the volumes of water, because through the experiment we found the difficulties to measure the level of the water in the tube. Besides that, the value displayed on the manometer is keep changing and not consistent. Thus, it was difficult to get an actual value of a pressure drop. Besides that, the formation of the bubbles in the flow meter also causes the error in the pressure drop reading, because the presence of the bubbles in the pipeline will increase the pressure drop and increase the frictional force to the flowing fluid. So we'll continue on the technical problems and error analysis. So through the experiment there are few errors has been addressed. For instance, while taking the reading with the manometer, the values of the pressure drop are keep changing and fluctuating. So this causes the device doesn't show the accurate reading, and this also causes the calculated head loss values are also become inaccurate. Moreover, since the values of the pressure drop keep changing and fluctuating, so we try other alternatives by changing the units of the pressure drop for every and each reading. So this causes the most of the reading are taken regardless of using the consistent units, and this may causes the error in the data obtained. Then the formation of the bubbles in the pipeline also causes the reading become inaccurate. The formation of the bubbles in the pipeline causes the extra frictional loss and pressure drop. So to prevent the formation of the bubbles in the pipeline, the water is allowed to flow for several minutes. So by this, the bubbles are completely removed from the conduit and also avoid the accumulation of the contaminants in the pipeline. Besides that, a very small leakage in the pipeline also causes the error in the reading. So there are a lot of technical problems and error encountered, so we try to minimize the error by repeating the experiment for several times and get the average reading.
So here we are to the final part of the video, which is the conclusion. So because our experiment is objective is to find the head loss, so we decided to talk about the factor that contribute to the head loss in the conclusion. So the first factor that contribute to the head loss is the internal diameter of the pipe. So as internal diameter decrease, head loss will increase. This can be proved back by the experiment A, which we see that the pipe with have a small diameter have a significant larger head loss compared to the other pipe. So the second factor that contribute to the head loss is the geometry of the fitting. And as different shape of fitting have different kind of K factor. So for example, 45-degree elbow have 0.75 K factor, while 90-degree elbow have 0.25 of K factor. And as they have different K factor, of course their fanning friction will be different, which will affect the head loss. And the third factor that contribute to the head loss is the sudden change of direction of the fluid. So as fluid will become more turbulent, they will consume more energy. This can be traced back to the experiment C, where we calculate the head loss for the contraction and expansion part. So next we also decided to include the industrial application in this part. So the first industrial application for fire fitting is it can be used to transport hazardous material in a long distance. It also serves as a protection for sensitive equipment at high pressure. And the second industrial application is the venturimeter, which is one of the flow meter that we use. It can be used in carburetor. We use it to measure the distribution of fuel and air in the vehicle. It also can be used in wastewater pipe because it is suitable for the SURI and viscous rate. And finally, the third application is for the orifice meter, which is also part of the flow meter. It's been used to measure the flow rate of a single state fluid. For example, we can measure the flow rate of oil or gas in the oil and gas industry.